Hello everyone, and welcome back to a new video in our modeling, analysis and design of pile foundation. Of course, if you are new to this channel, this is part of a video series, an ongoing one, which I will be linking on the top right, talking about everything you need to know from the theory to the implementation of pile foundations in Autodesk Robot. Now we are still stuck in the theory part because we need to cover this theory part before we can apply it in Autodesk Robot. So in today's video, we're going to understand some general principles about pile foundation, when we use them, what types of piles we have, and so on. So with that being said, sit back, relax, and enjoy the show. Alright, so when are piles even recommended as foundation? Well, piles are recommended as foundation in multiple cases as per the book Brajamdas. One of them is if you have extremely weak soil above strong soil, meaning the first some couple of meters of your soil is extremely weak and below it is a layer of strong soil. And in this case, if you want to do shallow foundations, your foundation would be big because the soil is weak, increasing the footprint of the structure and sometimes even the cost. So if that's the case, you would be able to reduce the size of the foundation by providing piles to the foundation that extend all the way down to the strong soil, enabling a better bearing capacity and better behavior. Now, this is usually the case if you have reclaimed land. This happens in some countries where there's a large beachfront and they want to extend their beaches by reclaiming land, because when you reclaim land, you're actually burying the sea, which means the top layers are not historical layers, which are actually might be weaker than the other historical layers. So yeah, that's case number one. Case number two is if you have a large loads without enough space for spread footing. Basically, in both cases, you can think of it as reducing the footprint of the structure. Because were you to make a raft foundation for this thing, you would extend the raft foundation multiple neighborhoods, which is not feasible. So if you have large vertical loads and limited spacing, then you would need to go for deep foundation, pile foundation. Another case of use here is you have large lateral forces, where friction and shear shears are not enough. You would think I could solve this with the retaining wall, and you are partially right. If you have a difference in soil height, then you can easily retain the soil, the higher soil, by placing a retaining wall. And we have some videos about retaining walls on this channel. I will link this in the top right. And basically what you have here is you have some pressure from the soil being applied on the retaining wall, as well as some passive pressure here. The pressure from the right to the left, from the high soil to the low soil, is higher than the pressure from the left to the right, meaning that there is a net horizontal force going to the left. This foundation needs to resist this sliding force, they call it, and you have two sources for that. You have the soil resistance itself, which could be friction and cohesion, and you could add a shear key to increase or improve the resistance to sliding. Now, sometimes it doesn't work like that because the difference in soil is so large, it just economically unfeasible. In that case, you would just pile foundation it, meaning that you would extend piles that kind of support the load via bending and shear action. And that's one case. Another case is this. This case, you have to have pile foundation because the retaining wall doesn't work here. And you would think, why? It doesn't look like a high ground. I mean, a retaining wall can easily cover that. And you are right, a retaining wall would cover that. However, it doesn't work due to practical considerations. What you see here is a excavation work for foundation of a structure in an area where there are other structures, meaning that you have an excavation work happening here, and you're not in the middle of the desert or in the middle of nowhere. No, you are actually in the middle of a suburb, meaning that you have structures on your left side and structures on your right side. Now, if you do not retain the soil, then the soil would, due to slope stability, the soil would start to be eaten away from here, causing all kinds of cracks in the nearby buildings, of course costing you a ton of money and a lot of lawsuits, which is something you don't want to do. Now you would think, okay, that's easy, let's place a retaining wall. Well, it doesn't work because when you want to make a retaining wall, you need to excavate and then do your retaining wall. So you're kind of defeating your purpose. You don't want any soil to be excavated here. So to do the retaining wall, you need to excavate soil. That's kind of counterintuitive. So what happens is, before we dig anything, we would hammer in piles here. So while the ground is still horizontal, we would hammer in some piles, cause you to have a perimeter like this, and then we'd excavate the soil. In that case, you just excavate the soil without having any slope stability issues, and no cracks with your neighbors. Another case is you have expansive or collapsible soil. Basically you can see that piles are well known when you have bad soil on top of good soil. It was in the previous slide, weak soil, strong soil. Now it's swelling soil and stable soil. The problem with swelling soil or collapsible soil is that there is vertical movement. And if you are placing a structure just on the ground, the vertical movement will cause cracks in the structure. If you place it on piles, then the piles are not moving because they are embedded in strong soil. And you can even place some spacing between the structure and the soil. In other words, piles would resist the upward and downward movement of soil, reducing the amount of cracks you would have here. The next case here is when you have tension on the soil or uplift, meaning that there is a tendency of an element in the structure to move up. This could happen due to horizontal forces or earthquake forces, where you apply horizontal forces which will be resisted by a couple force of compression and tension at the pile. This will cause uplift forces or tension forces on the element. It wants to be rooted up basically. And of course, soil cannot hold any tensile forces, so you need to resist this with a pile. You would think, wait a minute, how can a pile provide tensile forces? Well, due to skin friction, at least. If you have scour or earth erosion, you might need piles, because if you have scour and earth erosion, it would erode the soil below your ground. Of course, this is an extreme case here. It should never have reached this position. But I'm saying even if you have some slight erosion here, you don't care because your pile is embedded to the strong ground. Of course, here you should care because the scour is way more than you can safely consider. But I'm just showing you here an extreme case. So that is when we use pile foundation. For the pile types, well, you can divide them based on how they carry the load and based on the material and other things. So for example here, based on the material, you have timber piles and those are usually driven. You have steel piles which are usually driven. And you have concrete piles which may be driven or may be cast. This is a quick comparison table. You can even print screen it if you want and use it for your own reports. And in this case, you would have a comparison between wood, steel and concrete. Well, the cost of wood is low, it seems. Not really sure, it depends on where you are in the world, but I think it's generally low. Steel is high and concrete is somehow medium. Durability for timber is low because it's a biomaterial. It is susceptible to decomposition. Steel and concrete has high durability. Susceptibility to rot and insect damage, well, that's what I just said, so it's high in wood. Suitable for heavy loads? No, because the material wood is weaker than steel and concrete, so this only works for simple sheds and simple structures. Does it work for poor soil conditions? Not really that much. It still works, but in a limited fashion. And how do they carry the load? Well, they all share this by end bearing and friction. Usually timber piles are driven. Steel are usually driven, but they can be bored. And concrete is driven or cast in situ. Environmental impact, well, this is where I am not an expert here. Well, we shouldn't cut wood for piles, that's one thing, because of the climate change. Steel has also an impact on climate because it corrodes. And concrete seems to have a high impact because of carbon footprint. Once again, I took this from references. I am not a specialist in environmental impacts. One of the objectives you have when you design piles is to estimate the pile length. Now, to estimate the pile length, you need to understand, first of all, how the pile resists forces. Let me explain the way piles carry loads by the analogy of a pen and a fist. Imagine you have some strong sheet here. This is like, I don't know, steel or something. It looks like paper, but let's consider it to be steel. And you're also holding the pen in your fist, okay? So now somebody comes and wants to push the paper to basically go down. His force of pushing the pen will be resisted by two things. First of all, the sheet below the pen is going to provide bearing capacity, and your hand itself is going to provide friction. Because if somebody tries to push the pen, your hand is going to resist this push, which will provide friction. And that's exactly what happens in piles. The ultimate load carrying capacity of a pile is the load of the tip and the load of the skin friction. And in order to estimate the length of the pile, you need to know what those are, because all of them depend on the length L, so you need to understand them. And to understand them, we need also to understand how piles carry loads. Now, there are two types of piles and a combination. You have friction piles, load-bearing piles, and a combination of those. If you have a very strong layer and a weak soil, then the friction provided by the weak soil, and by the way, this and this are the same. If you have a strong layer or rock and a weak soil on top of it, then yes, the weak soil will provide you with friction, QS. But it is overshadowed by the strength of the tip of the rock. So the ultimate strength is QP, the bearing resistance of the tip, which is resting on strong soil, and you can ignore QS because it's relatively small. Even here you can see QS and QP, but still, because it's a strong soil, QU would be almost equal to QP. But if you have a pile that doesn't reach a strong soil, meaning that QP is weak, then you only have QS, which is a friction pile. This is just an approximation here. You could calculate QP and QS for all piles and just calculate and use them. Now for the pile installation methods, there are basically two methods. One of them is called the displacement method, and the other one is called non-displacement method. Displacement means to move something. So what is being moved? Well, if you have soil and you are having a pile into the soil, then if you are pushing soil away during the installation process of piles, that's a displacement method. But if you remove soil and then put the piles, so if you replace the soil, not displace the soil, then this is non-displacement method. So, for example, displacement methods would be hammering a pile inside the soil, meaning you have a pile and you are going to force and drive it into the soil without removing the soil. So basically you are pushing the soil to the sides and you are hammering in the pile. Now, if you basically come with an auger and you excavate the soil, so you open a path and then you put your stuff inside, for example, concrete, you cast it in place, then this is a non-displacement method. There are advantages and disadvantages and differences between those two methods. I mean, one of them, at least, is the bearing capacity and the friction. Because when you disturb soil and when you bore it with an auger, then the clamping force on your pile are not as much as the clamping force or the friction forces if you drive the pile into the soil. So this is one of the basic differences here. Anyway, you displace the surrounding soil when you insert the pile. Here you excavate the soil and just fill it with something. The soil disturbance here is high, which is a good thing. I don't know, like it says low, but okay, I understand that you're not disturbing the soil, but you're actually disturbing the soil because you're boring. So it depends on how you look at things. Noise and vibration, of course, driving a pile in is high noise because you're using a literal hammer to drive that thing in. For weak soils, it doesn't work that much because soils can cave in. And if you have obstacles, then driving a pile is not good. Meaning, look, if you have like a stone and you drive the pile in and it hits this obstacle, then it's going to be complicated to kind of break the obstacle. But if you have an auger and you face an obstacle, just drill through it, no problem. Speed of installation. The speed of installation for displacement method are usually faster because it's just driving the pile in one process. But if you use this auger method where you excavate soil, then you have multiple steps. Excavate the soil, pour in the concrete, wait for the concrete to set, and then close the... It's a long story. For the cost, if you are living in a country that has well-established pile driving techniques, then it is generally cheaper. Environmental impact, once again, I'm not an environmental guy, but here I think he talks about the noise and vibration, so I think this makes sense. Now for the pile capacity. The pile capacity is Q ultimate, which equals the Q of the tip plus the Q of the skin. And of course, one of them could be much more than the other, making it a bearing pile or a friction pile. But in this case, we are going to talk about both. The strength of the tip is equal to the area of the tip multiplied by the bearing capacity of the tip. Now, the bearing capacity of the tip is something we are going to be talking about in different videos because you have Terzaghis method, Meyerhoff's method, and Vesich's method. Each method has its own assumptions, so this needs to be explained in another video. What about AP? AP is the section area of the pile, including the soil plug, meaning the pile and the cavity. That's what it means. And that's a cool thing, by the way. If you have a solid pile, it would be AP, of course. And even if you have a pipe pile, this soil plug still plays a role. You know what a soil plug is? It's basically, imagine you have the pile, you drive it into the ground and then pull it out. When you pull the pile out, you will pull the pile and some soil with it. The soil plug is what you pull with it. And you can see that it still includes the entire area of the pile. Even here, you can argue that the soil plug is this thing. So I like to say that it's basically the boundary area, the bounds. Just take the bounds of the section and you can call it a day. How do we calculate this? Based on Terzaghis theory, you would have Q ultimate, which equals the Q bearing at tip. It is C and C, Q and Q, gamma D and gamma. Those are things you learned in soil mechanics. Now, I really urge you to check out your soil mechanics if you forgot that. However, I think it was not C and C stars, it was C and C and Q and gamma D and gamma. Now, those stars are there because you need to include the depth factors, because you are not at just depth of 1 meter on the soil. You are actually at depth of 30 and 15 and 20 meters, so those change. And a simplification can be done because the diameter of the pile is usually small in comparison to the other things, so you can flat out ignore it. And if you flat out ignore it, you have the Q of the pile equals C and C, Q and Q, where AP is, of course, the area with the plug, C is the cohesion, QP is unit point resistance, Q dash is effective vertical stress, and NC and NQ are the factors. Now, I will show you an example about this later, but for now, we need to understand that this equation exists. For the friction resistance, you can see QS equals summation PLF. Now, this seems to be odd. Allow me to explain this one step at a time. So let's say you have a pile, all right? And this pile is like this. And let me say or assume that this pile provides a certain friction stress. There is an ultimate friction at the pile, okay? So this pile provides F, which is friction per unit area, N per meter square. The amount of friction the pile can withstand per meter square. So you'd think that's easy. If I have F, of course it's the friction on the side area, then all I have to do is to multiply the area of the side of the pile multiplied by F to get the friction resistance of the pile. And that's true, by the way. I totally agree. Now, how do you find the side area? To find the side area of an element, you need its perimeter and its length. So the side area of a cylinder is the perimeter of the circle multiplied by the length. And that's what happens here. You can see P and you can see L. So it seems that according to what we were saying, the friction resistance should be P, L, F. But it seems that's not the case. It seems that there is a summation here, summation P delta L F. And the question is, why is there a summation? What's the meaning of that? Well, the problem here that you are facing is that F is not constant. F changes with the depth, and specifically changes with the amount of lateral force on the pile. Because if you remember your physics classes, you know that friction is basically N and mu. Like, you know that friction forces is a factor mu, which is the friction factor, multiplied by the N, the normal force to the surface. And this normal force changes with the depth of the pile, meaning at top you have small forces, and the deeper you go, the more the normal forces grow because of the lateral soil pressure, which means that in the end, this friction coefficient is not constant on the length of the pile, but depends on the depth of the pile. And that's the reason why we need to segment the pile into pieces, like piece number 1, piece number 2, piece number 3, as an approximation, and say that the friction on piece number 1 is constant, despite the fact that it isn't, and piece number 2 is constant friction, piece number 3 is constant friction, piece number 4 is constant friction, despite the fact that it's not constant. But that's the best thing you can do. Of course, the more segments you have, the more accurate your calculation is. And that's why you need to add those segments together. Summation P delta F, because your segment is summation P delta LF, because your segment is at delta L. So the side area of a segment is P delta L multiplied by the friction of that segment in the summation. In the end, to find Q allowable, you take the ultimate Q and divide by the factor of safety. So yeah, that's a quick introduction about piles, when we use them, what the types of piles are, how the resistance comes, and some basics of how to calculate the bearing resistance or the resistance in general for piles. So with that being said, thank you very much for watching, and before I finish, I want to give a deep foundation-sized shout-out to my dear channel members in the contributor level and the helper level whose names are going to be shown on the screen. I want to thank them from the bottom of my heart, as their support of the channel is priceless to me and enables me to provide you with videos hopefully on time and with a certain quality I try to achieve, and for that I am forever thankful. In the end, I hope that you enjoyed the video and you found it beneficial. If you have enjoyed the video, then please consider liking, sharing, subscribing, commenting, and so on, especially subscribing because it helps increase the reach of my channel. As per usual, This is the Civil Engineering Essentials channel, and we'll catch you in the next video. Bye bye.